the universe expanded unquestionably, engaging endlessly out more. First-rate length after this period, it drove forward to grow anyway at a more lazy cost in the quit changing over into the universe we focus on as of late. That is the inflationary speculation of the collectible enormous effect, the generally conspicuous and by and large saw hypothesis of how the universe started. At any rate, for several physicists, this head hypothesis does not unequivocally paint the creation of our universe, suggesting that the universe existed before that, expanding unendingly into the past as well as into the future. Even as the universe is extending nowadays, it became contracting early on before the tremendous explosion. In this view, the gigantic explosion isn't exactly a bang but rather a leap, a second even, while the contracting universe traded ways and yet again went out to make us spread out through their speculation. The universe could need to evade with continued progress, like less being prevented by a breakdown inside the distant future. Then another jump, a couple of physicists proposed this might be perpetual. This contrasts with the norm cosmological view in which all matter started with an enormous bang. The top-notch physicist Brian Cox discusses the hypothesis of how things seem to suggest that something can't emerge from nothing. Adding to the pressure, the James Webb Telescope has made disturbing revelations that conflict with the idea that the gigantic explosion was the beginning of the universe. These revelations bring up the question: if the colossal blast wasn't the beginning of the universe, then what was? The possibility that the universe had a beginning or a moment with no previously has roots in George Lemaitre's 1927 proposal. However, it's far from a universally accepted situation. The length of astronomical history barely ties to the hot wide bang that depicted our essential universe. While a significant portion of cosmic researchers, even a minority of experts, believe the tremendous bang is the earliest reference point, the definition does not necessarily coincide with the creation of life as we know it. In reality, there might be considerable proof suggesting a non-solitary beginning of our universe. We never arrived at these conclusions based on no clear start or excessively high temperatures. Our universe is better described through an inflationary length that occurred before the enormous blast. The gigantic explosion is the endpoint of what transpired during this period of growth. During this growth, the universe was essentially void, no debris, no photons, simply void. Space itself was filled with a massive amount of energy uniformly. Over time, this energy transitioned, expanding rapidly in a consistent pattern. As the universe slowed, these changes led to significant expansions while new measurable changes emerged. This superposition of uncertainties across scales is a defining feature of cosmological expansion. For conflicting reasons, living in an expanding universe might lead to encountering local areas where expansion halted or regions where it delayed significantly. In short, attempts to track what happened closer to the beginning of a massive impact might find small areas, possibly no bigger than a human scale size, or even considerably larger. Energy in space then transforms into matter and radiation, with this transformation happening rapidly. It takes form quickly, but not instantly, as the energy itself converts into particles and photons, raising the temperature from a few degrees above absolute zero to around 20 Kelvin. The considerable energy changes near the speed of light, with all particles behaving as radiation, regardless of being massless or massive. This process, termed reheating, signifies the end of growth and the start of a new phase known as the New Big Bang. As growth continues, a tremendous shift from previous states occurs. When the current Big Bang starts, the expanding universe slows down after the initial burst of progress. In an inflationary universe, areas of space grow exponentially with greater distances. As progress ends and the new Big Bang begins, farther regions move away, making visible regions more limited over time. This means that in the expanding regions surrounding us, no such decline in expansion rate is observed. Under this expansion, space between objects doubles over specific intervals. As time passes, the distance doubles continuously once the tremendous blast starts. This adjustment occurs because the growing universe slows after the initial burst. Before the colossal explosion, encountering growth with nearby regions means that areas where growth ends will accumulate antimatter and radiation, making them slower than the now growing regions, leaving one in an expanding area as a normal occurrence within spacetime. Regions where powerful Big Bangs occurred will drift apart from areas where growth continues, making them gradually disappear from view within the normal inflationary model. Because the inflation rate changes, there is a slight chance that any universes with distinct warm Big Bangs will never converge. The area where we reside becomes fortunate, as growth ceases for us. The power typical for space itself transforms into a dense and nearly uniform distribution of particles, with initial flaws and deviations stemming from the quantum changes that existed and were distributed across the universe during growth. Quantum instabilities, contrasting initially, lead to overdense areas while poor energy instabilities become the most significantly underdense regions. These act as seeds for cosmic structures. We can't observe these density instabilities as they were during the universe's early stage after the tremendous blast. There are no discernible marks we can access from that early period. However, we can extrapolate back to understand the primary density instabilities, aligning them with the narrative of cosmic growth. The temperature instabilities are recorded in the cosmic microwave background, CMB, providing evidence of how the colossal explosion started. Yet, anomalies exist within the CMB and our modern cosmology, indicating something missing. For anomalies summarize these gaps. First, on predominantly large scales, the universe doesn't behave as expected. The light from the CMB is being lensed between us and the CMB, acting like a massive lens, distorting the light's amplitude. The extent of this lensing isn't always consistent with our current model, representing a significant mission for cosmology. Second, unique temperature patterns contradict the expectation of uniformity in the universe's earliest stages. The idea that the universe should have started smoothly results in different anomalies. Third, the rate of the Hubble constant, describing how quickly the universe is expanding, varies depending on whether measured from the CMB or nearby stars. These irregularities suggest we are missing something significant in our understanding of the universe. One proposed solution comes from loop quantum cosmology, originating from loop quantum gravity, where gravity itself consists of particles called quanta. In this framework, there's a smallest scale, suggesting the colossal bang couldn't exist in a universe described by this standard. Instead, the universe might never reach a minimal dense state near the Big Bang. In loop quantum cosmology, as the universe became minuscule, quantum corrections introduced a negative pressure causing a bounce, rather than a singularity. This indicates that our universe might have started from a contracting universe, expanding again like a phoenix from the ashes. The idea of a big bounce isn't entirely new. Loop quantum cosmology provides a mathematical structure supporting cyclic time, akin to the concept of a grand leap. If loop quantum cosmology holds, the early universe might have had distinct energy and density. This scenario would alter the CMB, appearing as subtle temperature variations across the sky. These variations, measured through quality energy range, offer compelling evidence of the universe's origin, further guiding the possibility of a bounce. Loop quantum cosmology presents a convincing opportunity to revisit the modern Big Bang theory, potentially resolving long-standing anomalies in cosmology and offering insights into the universe's origins. It also provides a plausible explanation for the temperature discrepancy between the two hemispheres of the CMB sky. The model aligns with the key peculiarities found in the CMB, such as unusual large-scale behavior and the lensing effect. Dr. Vetko from the National Institute of Advanced Studies suggests these anomalies might not be mere statistical errors but arise from quantum gravity effects at the universe's inception. The idea that the universe started in a grand leap has been proposed before, but its validation requires further investigation. Vast variance presents a challenge, as our observations might be limited to specific parts of the universe, complicating our understanding. Physicist Dwayne Johnson, a co-author of a significant study and a professor at a notable institution, highlights the difficulty in endorsing such theories due to their vast scale. However, incorporating recent theories like loop quantum cosmology and its implications maintains hope for resolving novel cosmological issues. Despite these advancements, a fundamental question remains. Did the universe have a beginning at all? Advocates for a universe with a beginning argue that it did, raising questions about the nature of the event that initiated everything. On the other hand, cyclic cosmology suggests an eternal universe, continuously present and evolving. Physicist William Kenny from the University of Buffalo identifies a primary flaw in this idea: entropy. The degree of disorder in a system increases with each cycle in cyclic cosmology, implying a starting point that conflicts with the notion of an eternal universe. The universe undoubtedly expanded at an accelerated rate initially, continuing to grow at a slower speed later, eventually evolving into the universe we know today. This is embodied in the inflationary speculation, the most widely accepted hypothesis of the universe's origin. However, some physicists argue that this hypothesis does not accurately depict the universe's development. They suggest that the universe existed before the Big Bang, expanding endlessly into both the past and the future. While the universe is expanding today, they propose it was contracting before the Big Bang. In their view, the Big Bang was not a unique event but a transition point when the contracting universe reversed course to expand again. According to this speculation, the universe could avoid a definite beginning and instead continue to evolve endlessly, less hindered by a collapse in the distant future. Brian Cox, a prominent physicist, challenges the idea that things emerge from nothing, complicating the traditional view that all matter started with the Big Bang. Furthermore, recent discoveries by the James Webb Telescope cast doubt on the idea that the Big Bang marks the universe's beginning. These findings raise the question: if not the Big Bang, what did mark the beginning of the universe?